Good morning. Welcome to Anthill Inside. I'm Tink, I'll be your MC today. And for those of you who have been with us through the fifth elephant, the next few minutes are going to seem very familiar. First, I'd like to point you to the toilets. The closest toilets to this room are out that door and just down the hall. There are also toilets in the dining area. You can make use of both of them. You may have noticed when you sat down a sheet on your seat. That's our morning feedback form. If you didn't see a sheet on your seat, then you're going to be getting an email. Actually, you're all going to be getting an email with a link to our feedback. As you've heard for the last 2 days, we really like to hear from you, so please do fill in your feedback forms. If you have eaten here already, you probably already know that you can use PayTM or food tokens at all of the food vendors today. The food court has a variety of foods for pretty much every diet we can think of, so we hope you'll find something tasty to eat at lunch. The merchandise counter is in the lobby and will be open later. If you pre-ordered a t-shirt or you want to get yourself one, please stop down at the merchandise counter. We have also got t-shirts from Fifth Elephant, so if you want to pretend like you came to the conference and you didn't, you can do that. Intel today is going to host a workshop on deep learning tools and framework in room 1 as part of Anthill Inside, so please check your schedule for that. And there is a training workshop on NLP, which as a non-AI person, I always think of as neuro-linguistic programming, but of course it's not. It's natural language processing. That's tomorrow. And tickets are 3,500 rupees. You can buy them online, or if you want to buy them in person, you can stop by the registration counter. And I think that's all of our announcements, and it looks like our speaker is just about ready. Everything okay over there? They need one more minute. So, since Lo-chan's not here today, guess what? Let's do stretching before our first session. Everybody stand up. See, what you guys don't realize is I'm a circus performer and teacher. I stretch a little different. I'm not gonna make you close your eyes. You do not have to breathe, although I do recommend you continue to breathe. We're gonna put our right hand up in the air and wave it around. Hi, good morning. Oh, it's so nice to see you all. Let's do that with the left hand. Up. You could turn around. Wave to the people behind you. Yeah. Can you wave a foot? You guys don't have as much room as I do, so you're probably not going to get it out that far. You can try kicking the person next to you. You can try shaking the person behind you. Loosen up those hips because they're about to sit down. All right, you can sit. See, my stretching's a little different than Lo-chan's stretching.
Yeah.
All right. I think they're ready. So, our first talk this morning is a tutorial about a new paradigm in machine learning called deep reinforcement learning, which is a sort of more human way to learn. Now, I don't know anything about it, but Vikas Rekar from IBM is an expert, and he's going to walk us through this. Morning, Vikas.
Thanks. Okay, thanks for the invitation, and I think a disclaimer, I'm not an expert, so that's why it's a tutorial talk, otherwise I would have given a more expert level talk, yeah? So just a show of hands, how familiar are people with deep kind of reinforcement learning here? Does a Markov decision process, does anyone know what's a policy gradient? So I'll kind of try to tune it to that level. I think I'll try to keep it fairly basic, yeah? Since it's going to be a weekend morning, I didn't want to go too much into the details, but it's still going to be a bit fairly math heavy, yeah? So just bear with me. So at least the title has split it into 2 parts. So what's called reinforcement learning, and then there is something called deep reinforcement learning. So the first half of the talk, around 20 minutes, will be just getting the notation of the reinforcement learning. And then towards the end, we will kind of shift gears towards the deep reinforcement learning. And mainly we'll focus on one algorithm which is called as a policy gradient, and we'll try to derive that, right? So I don't plan this tutorial to be fully exhaustive. So this is just to give you some pointers to get started from where you can read up further, yeah? So essentially the motivation for deep reinforcement comes from this fact, right? As humans, we kind of learn by interacting with the environment. Think of an infant trying to walk, or you're trying to learn to balance a bicycle, yeah? So no one explicitly going to teach you, given examples of that. Okay, you're sitting in the right position, so you get a label 1. You're sitting in the wrong position, you get a label 0, etc., right? So you essentially, you go deep dive into the environment. For example, you try to walk, you fall down, or then you kind of get hurt, that's your reward, -1. Or you kind of get up and suddenly you know that you're trying to figure out the balance, so you get reward of +1. And then you kind of slowly, you get a sense of what it means to walk, or what it means to ride a bike, by just trying out things, right? So that's essentially where humans are learning. No one giving you, there's no explicit teacher as such saying, okay, this is 1, 0, 1, 0, 1, 0 in a conventional machine learning framework, yeah? And that's essentially going to be the motivation for reinforcement learning. And so the couple of things here, right? As humans, we are acutely aware of how our environment responds to what we do, right? That's the key thing here, right? We are acting in an environment, we do something, and we kind of get feedback, right? So we know how the environment is responding to the actions we take. And the second part is the most important part, right? We seek to influence what happens through our behavior, right? Once you get the reward, I kind of now control how I should do my actions so that I can get my rewards better, yeah? So essentially, a reinforcement learning is just a computational approach to kind of formalize this notion of learning, yeah? And this is what we call as learning from interaction, yes? So in contrast with, you have this supervised learning where you're learning from labels, then this unsupervised learning, no labels. So it's kind of, the way to think is that this is a way of learning from interaction with the environment, yeah? So technically a reinforcement learning agent learns from interaction with the environment to achieve a desired goal, yeah? In summary, this statement essentially, I think the rest of the slides are just going to be, how do I mathematically concretize this one statement, right? What is a mathematical formalism for just to make sure, how do you kind of model this statement? Learn from interaction with environment to achieve a desired goal. So there are kind of, I mean, I won't go into a lot of applications. There are quite a lot of applications, like for example, where this motivation is coming from, but I started with the way the humans learn as a motivation, but that's what not we're interested in. We're actually interested in a lot of various problems, right? For the classical example is learning to play games, control systems in robotics, or even recommender systems, right? Can be cast in the in a reinforcement learning framework, or even trading, or at a very high level, even some standard supervised learning problems, kind of, if your problem with certain non-differentiable loss functions can also be cast as a reinforcement learning problem, yeah? So it's kind of it's a very new it's not a new paradigm, but it's a very powerful paradigm if you somehow make it work, yeah? Because almost any problem you can think of, I mean, you can cast it in a reinforcement learning problem, and that's what I want to get to you today, right? I'll give you the basic formalism, and you can think of your own setup, whatever problem you have, and how do you formulate in that. And then there are certain standard algorithms which you can to crank the machinery. So I'll just briefly flash a couple of examples before we get into the details, right? So this was in 2013, I guess, where DeepMind showed that you can actually learn to play Atari games just from raw pixel values, right? And so the examples I'm showing are some kind of success stories in deep reinforcement learning rather than reinforcement learning. So reinforcement learning has been there for quite a long time, and but it was not successful mainly because of this. Till deep learning came in because of this infinite state space, it had a lot of computational issues. But after a couple of these, since 2012-13, there has been kind of a tremendous progress in deep reinforcement learning, yeah? So probably, I think let me make a comment. I think these are the two talks, the way I've arranged, I think these are probably currently the most hot areas in deep learning. So one is the deep reinforcement learning, and after this, the second talk, which would be the GANs, right? Probably that's why I think you can see probably, if these are almost on the cutting edge of the currently in the deep learning setup, yeah? So at least, yeah, so what I want to point out is that to learn this, all you need is just the pixel value, right, of the Atari game, and they were able to figure out how to play the game, yeah. Then the Google's AlphaGo, which defeated the Go, was essentially another I think this was in 2017, right? This was again purely based on kind of the deep reinforcement learning framework. Then, so there are other examples, a lot of examples in robotics, right? How do you make a creature jump in a terrain? How do you try to control it? Those are kind of a lot of examples coming up in robotics. And this is an example in Berkeley. There is something called as a preschool for robots, right? Essentially, the way humans, like kids go to preschool, you can have like robots go to preschool where they just keep trying learning things. And essentially the whole loop, the closed form loop is a reinforcement learning loop where they keep trying, how do I lift here and keep it there? How do I grasp something, yeah? And essentially they're just sitting and trying and doing that for days together. That's essentially, but we'll come to the formalism later, but that's one example to think of, yeah? So I'll also give one example in a recommender system, and this is exactly also what I'm trying to, this is some work going on in our labs which I'm trying to cast even a recommender system as a deep reinforcement learning problem. Say for example, you say I'm looking to buy some dresses, you get some items in the catalog, then you say the user actually clicks on a blue dress, then it shows some blue dresses, then again the user converses, say show me only sleeveless, then again it picks up sleeveless dresses, etc. Yeah. So this is the way you again see that you're interacting with the catalog, you're making some actions, the system is showing you some results, and you're getting a reward in the end. What is the reward? Someone adds that item to your cart, right? Again, how do you formulate, we'll come to that, but again this sort of simple multimodal conversation system or learning your recommendations can itself also be cast as a deep reinforcement learning problem. Yeah? So I'll also point out to this thing side called as OpenAI Gym, which is essentially a lot of these examples which I'll talk about are coming from there, which is essentially a series of video games. You think of it as more of an test bed to test your deep reinforcement learning algorithms, right? So you'll get an example of some game where there is some AI agent which is one side, and you are trying to your reinforcement learning algorithm to kind of win the game. Yeah. So there are a lot of games in that. Yeah. Okay. So that's the introduction. Now I think we're going to do a deep dive into the deep reinforcement learning framework. Yeah. So I'll again come back to the formalism, which is an agent learning from interaction with the environment to achieve a goal. Yeah. And this is what we want to formalize. What is an agent? What is an environment? What do you mean by an interaction? And what is a goal? And how do you achieve that? Yeah. So as I said earlier, so this kind of, there is this whole concept of supervised learning where you're given explicit labeled examples to learn. Then there's unsupervised learning, and what we're talking about, the third paradigm, which is called as the reinforcement learning, where in a lot of examples it's often impractical to obtain labeled examples which cover all possible scenarios. That's why it's a very natural way to kind of formulate problems in the reinforcement learning setup. Yeah. So before we even understand deep learning, we need to speak the jargon of deep learning, right? If there are, I mean, if you think these are all very familiar, then please raise your hands, then I won't cover. But this is exactly what we're trying to cover, right? What is an agent? Environment, state, action, reward, policy, return, value function, model, right? These things, any problem you think of, if you can actually map your things to these things, then you know how to cast a problem in RL framework. Yeah. So we'll just go one by one, and that's essentially the main talk. Yeah. So my references for these are two things where I prepared the talk. So one is this Richard Sutton's book on reinforcement learning. There is a new edition. I think the book is pretty old now, so he's writing a second edition of the book that is freely available online. And if you want to go deep, chapter 1 to 3 are the things where you'll get a good sense of reinforcement learning, right? But after 1 to 3, you can actually stop. After that, it's all classical reinforcement learning. Then you probably deep reinforcement learning, hardly there are not many textbooks out there yet. But kind of the example I'm taking is from this Karpathy's blog on the deep reinforcement learning. That's the working example I'm using to explain some of the concepts. Yeah. Okay, so let's dig deep now. Yeah. So essentially we are trying to formulate this agent-environment interaction. Yeah. So again, we'll reiterate the same thing. So an RL agent must be able to do three things. It must be able to sense the state of the environment. Yeah. It must be able to take actions that affect the state. And the third one, the agent must also have a goal relating to the state of the environment. Yeah. So this is the diagram, I think probably try to memorize, right? This is what we'll have to keep using back and forth again. Yeah. So there is three things here. So the agent and the environment. Yeah. So the agent is the learner and the decision maker is called the agent. Okay, I have an example. Okay. and the environment is the thing it interacts with is called the environment. So an agent is someone you're trying to learn, right? An RL agent, some trying to make the action. Environment is something which is completely outside the agent, yeah? That's how you think of the environment. So the boundaries are all depend upon the problem. It does not necessarily mean that the environment and agent can also be the same person or it can be the same robot. It's essentially where you demarcate, I have to take an action. Whatever is outside the agent is environment, yeah? So the agent actually takes an action, yeah? The agent selects an action to perform, yeah? It could be here that I'm trying to get up or trying to walk, right? That's an action. So the environment actually gives out a reward for the action, right? You take some action and you get a reward out. And the state is essentially, once you get that reward, the state gets modified, yeah? So we'll again reiterate these three things, but things you need to remember are action, reward and state. So the agent takes an action, the environment gives you a reward, based on that the state changes, then again the agent takes the next action, and this is a control loop or this is a closed form loop that keeps continuing, yeah? That's the basic formalism of an RL form. So we're going to use this example throughout, yeah? So this is what is called as one of the games in the open gym. It's called the Pong game, yeah? So let's spend some time on what is that we are trying to do here, yeah? There is a video here, but it does not work, so let me just directly go to this part, yeah? So this is, think of this as a classical ping pong, right? Whatever, your table tennis. So what you see that there are two paddles here. Let me see if I can, yeah. So this is one paddle here, there's another paddle. These are two ping pong pads, yeah. So this paddle is controlled by an AI agent. That's essentially the game who is controlling it, yeah. And this is, you are playing this paddle, yeah. So your goal is essentially you can move the paddle up, down, etc. And there is the ball here, yeah. So you essentially take this paddle, hit the ball, and it goes up here, and then this guy hits back, and that's how you play the game. You're essentially playing a ping pong on this grid of, say, 200 cross 100 pixels, yeah. And every time, say, you hit this ball, let's say the AI agent or the game cannot intercept it, and it goes out of the boundary, then you win, yeah. So if you essentially, this guy hits it, and it goes out and you cannot intercept it, then you lose, yeah. So if you hit once, you get a reward of 1, or think of you lose, you get a reward of 0. So essentially there's a counter here which says how many wins you get, right? And that's how the game proceeds. So essentially, classically it's just a TT game, table tennis game, right? You're just passing the balls anyone. And the goal here is that I need to figure out how should I hit, yeah? So the green guy, what you see, right? That is the RL agent. So I'm going to play this game for many times, many 200,000 times, and figure out how to play this game perfectly, right? Without any supervision, yeah? No one is going to tell me how to play the game, right? You have the game engine which is you're playing with. You think that you're going to play with an opponent, yeah? And somehow you're going to play around and then figure out how I'm going to win, yeah? So that's the setup. So that setup is pretty clear, right? So any issues on that, okay? So the agent plays one of the paddles and the other paddle is controlled by the game, and your goal is actually to learn how to play the game, yeah? So that's the reinforcement learning framework. Let me just briefly mention one point that if you want to learn this, right, the AI engine, which is the orange one, it cannot be a perfect engine, right? If it's a perfect engine, that means that you're never going to win, and you're never going to get any feedback on what kind of actions do I need to make to win. So typically, generally, this game system is also an imperfect AI system, right? So you have some chance of winning, but you are going to play around to figure out how to win and lose. So you're going to start playing, you're going to win some, you're going to lose some, and eventually you want to learn a policy or a strategy how I'm going to win against the opponent, yeah? If the opponent is perfect, it's nothing. I mean, you won't even get a chance to learn anything, yeah? Unless he explicitly teaches you. Okay, so in this context, okay, so I'll tell, coming again, what is the agent? Agent is the green paddle, yeah? What is the environment? Everything other than the green paddle. So the entire array of the whole game, that is your environment. What is your action? I can take either the paddle up or down, right? Essentially I'm moving paddle up and down to intercept the ball. That's why that is the action. So what is the reward? Either I win the game, I lose the game, or nothing happens because is just in some state of the game. And what is the next state? State is essentially the whole image, right? So you get the ball at green, you give one smash, it goes around. and then you get some reward, and after that the state changes, which is essentially the new position of the ball. Yeah? So that's how you abstract this problem in this setup. So now we'll start introducing a little bit more notation here. So we call the action as an AT, yeah? We call the state ST and a reward RT. Yeah? And a game essentially is a sequence of this, right? You start with state S0, you get an action A0, you get a reward R1, state changes to S1, you take an action A1, you get a reward R2, you keep continuing till you hit a terminal state. And what is the terminal state? You either win or you lose. At that point you stop, the game restarts, you continue. Yeah? That's essentially how you're playing the game. And this is a mathematical abstraction to that gameplay. Yeah? So again, I'll reiterate a little bit more. So the agent receives a representation of the environment which we call the state, ST. Yeah? And the state S belongs to this capital S, which is the set of all possible states. Yeah? On the basis of ST, the agent selects an action AT, which is also belongs to some space. Yeah? One time step later, as a result of the action, the agent receives a scalar reward RT plus 1. Yeah? Again, so this is a little bit, if you look at the literature, there is some confusion between RT and RT plus 1, but I prefer this notation where you get ST, you make an action AT, after one time step you get a reward RT plus 1, and then the state of the system changes to ST plus 1. Yeah? So that's your closed form loop. Yeah? So little bit on how we want to do is actions, again to generalize this, actions can be any decisions you want to learn to make, right? So anytime you think about problem, you need to think what is the action, right? What is my action? Here the action is very simple, I move the paddle up, I move the paddle down, but okay. And state, what is state? State can be abstracted by anything you think the action has to be influenced by. It does not have to be a perfect everything, right? It can be a simple thing, what set of features you think will be responsible for the action, right? It's all the game of how you model your state. Yeah? And in the end, the agent's goal is actually to maximize the total amount of reward it receives over the long run. Yeah? But I won't formalize this statement yet, that's what we'll do in the next couple of slides. So again, we'll come to this Pong example, right? So what is state? Now more precisely, state is nothing but this 210 cross 160 cross 3 RGB image. Yeah? So again, this is how we'll be, where each pixel in the image is some number between 0 to 255. So think as this roughly 100,800 numbers is your state, yeah? Which is what you want to do. Yeah? Your state is a vector of 100,000 dimensions, which is I just flattened this 210 cross 160 cross 3 image into a long vector. Yeah? What is action? Action is either binary, up or down, right? There are only two possible states. And what is the reward? Reward can be three things. +1 if the ball went past the opponent, -1 if we missed the ball, and 0 otherwise. 0, most of the time you're playing it will be 0, right? Because nothing is happening, but only at certain points you either win or lose, and that's when you get the reward, right? And the whole point is to figure out how do I get this +1s a lot. Yeah? That's essentially. So your goal is essentially to decide how should I move the paddle up and down based on what I see in the image, so that I get lots and lots of reward. Yeah? So before I move into something, I'll just briefly formalism called, so you probably have heard the term Markov decision process. And a Markov decision process or a MDP is another RL task with a certain special property called the Markov property. Yeah? So what does it say? Yeah? So this is essentially a way of kind of simplifying our state dynamics. So what does that mean? That I take some action, I get a reward, my state changes, right? Something happens to the state, which is essentially what I'm showing you here, right? So ST plus 1 is a new state, RT plus 1 is a new reward. In principle, this change can depend upon the entire history, right? You can go all the way back to your game or whatever, everything it can depend, right? So Markov assumption states that it depends only on two things, right? Which is essentially your previous history, which is ST and AT, the last state, yeah? The one example which I find it very interesting to think is, think of playing the game of chess, right? So chess is again a classic, you can formulate in RL framework, but anytime you want to make the next state, so all that you can do is depends upon the current state of the board, right? You don't have to know how you came to that board, right? It really does not matter whether you took an action from there, there are multiple ways of coming to that state. But once you are in that state, that's all it matters. Based on that, I can figure out what should be the next action and reward I should take. Yeah? That's essentially the Markov property. Yeah? And I think most of the problems you see kind of implicitly assume this is the Markov assumption, yeah. Even though the Markov assumption may not be true, it makes sense to actually, okay, actually formulate this as the Markov decision process, yeah. Okay, so now coming to we need to speak the basic RL vocab. So we know what is an agent, we know what is an environment. Agent is the paddle, environment is your entire grid, state is actually the pixel values, action is move the paddle up and down, reward is +1, 0, -1, yeah, that's the reward you get. So now we come to the other 4 things, which are policy, return, value function and model, yeah. So once I get these 4 things, I think you'll have a clear understanding of what is a reinforcement learning program, yeah. Okay, so we now come to something called as a policy. So at a high level, policy is something, what is the action you want to take here? I mean, abstractly, what is it? I want to decide whether I want to move the paddle up or paddle down. But at each step, the agent has to implement a mapping from state to an action, right? Given a state, that is the pixel, given this current, how the current state of the game is, I want to decide what should be the action I need to take. Whether should I move up or not. That formalism, the way of mathematically writing that is called a policy, which is what we use the notation phi of A given X. Given that I am in state S, what is the probability that I will take an action A? Yeah? Given that this image, what is the probability that I will move up, or what is the probability that I will move down? Yeah? So most of the deep reinforcement learning will use this notion of something called a stochastic policy, right? Which is essentially you, rather than taking a deterministic policy whether I can move up or down, all these compute is some kind of what is the probability that I should move up, what is the probability that I should move down, and you start sampling for it, right? So if you say probability of moving up is 0.9, moving down is 0.1, you actually toss a biased coin with probability 0.1. If it is head, you take that action, otherwise you go, right? And it's actually looks very simple, but there's a very strong reason why you want to use stochastic policies, because you want to encourage a lot of exploration. So if you don't use stochastic policy, you're always taking the best action, you're not encouraging too much of exploration. So you want to take the best action most of the time, but sometimes you also want to take other actions so that you can figure out some other possible ways of winning the game. Yeah, that's why the whole notion of a stochastic policy becomes important. So that's the probabilistic formulation. Okay, so in this, what is it, right? So in this game of Pong, it's quite simple. It's the probability of moving the paddle up or down, right? Which is probability that the paddle is up, or the probability that y is equal to 1. Yeah. Given the current image, which is this 210 cross 160 cross 3 image. So essentially, I'm trying to learn a function from this 100,000 numbers to a probability which says whether I should be up or down. Yeah? That's all there is to what is a policy. So we figured out now what is the policy. Yeah? But now comes to the question, okay, I know what is the RL framework, I know what it means to be, what's the policy. Now, how do I learn this policy, right? What is the formalism you can give me, or what is the mathematical machinery you can give me to learn the policy? And for that we need to bring the concept of a return. Yeah? Can you see, I can't see the time there, I just want to make sure I'm right on time. Yeah. Oh, so this is a bit frozen here. Okay. Okay. So the agent's goal actually, so there are 3 things, right? Goals, rewards and returns. Yeah? So this is what we'll walk through. Yeah? So again, at a high level, the agent's goal is to maximize the total amount of cumulative reward it receives over the long run. So you saw that earlier, every time you take an action, you get a reward, right? But what we don't want to do is we don't want to maximize we don't want to decide our policy to maximize our rewards, because they are almost instantaneous rewards. They're not long-sighted, right? What you want to do is you want to maximize the probability that eventually you're going to win, right? So that's what we call as, we need to formalize this notion of what is actually a return. Return is the bunch of rewards you get over the long run, and not just the immediate reward you want, right? Because you are just started with you're playing 1 or 2 games, you get a small reward and you don't want to base on that. Yeah? So, and that essentially comes to the most crucial step of modeling RL framework is actually, the way to think is that you have some goal, right? That's what I say, goal. Goal is I want to win the game, yeah? And the only knob you have to make sure that you win the game is how you specify your rewards. So all the kind of the creativity comes in, how do you specify your rewards so that eventually by maximizing this cumulative rewards, I reach my goal, right? If these rewards are ill-specified, or if you're not specified in the right way, it will try to only maximize that. It has no goal in mind. The mapping from goal to rewards is what you essentially have to play around with. How do you do that? Yeah? So before I continue give them more notation, I need to kind of define two kinds of tasks people talk about. One is called as the episodic tasks, and the other is called as a continuing task. The example of Pong I gave you is an episodic task. Yeah? An episodic task has a natural notion of a terminal state, that I start playing the game, I win or lose, and I stop. Boom, I again restart. I start playing the game. So every one trajectory of a game is called an episode. And then you play multiple episodes of the game. As opposed to a continuing state, there is no natural kind of time stop. You just keep on, like walking, or there's no way that you figure out walking or some robotic manipulation tasks. So there are other tasks, but we won't talk too much about the continuing tasks. I think for this tutorial, we'll be mainly focusing on an episodic task. Yeah. And this is how an episodic task would be for the Pong game, right? So you have this state with just the image, right? And each time you take an action, either you go up, down, 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 up, up, and eventually boom, you either win or lose. Yeah. So when you win, that is one episode. So what I shown you are 4 different episodes of the game, right? You start playing the game, you take some actions, you win. Then again, start playing the game, you take an action, then you lose. So you'll keep repeating. These are called episodes of the game. Yeah. So now we'll define this notion of what is a return for an episodic task. So for that, what you have is this notion of time steps, right? At any time t, you took an action at, then you got a reward at plus 1, and from that you continue playing the game, yeah? And then you got this series of reward, which is rt plus 1, rt plus 2, rt plus 3, till you hit the terminal state. Yeah? And return is nothing but just a function of these sequence of rewards. Yeah? That's it. And it can be, technically it can be any function, but the most commonly used function is just the sum, which is essentially a sum of these rewards, right? So in our Pong example, it will either be 1 or minus 1, because you start off 0, 0, 0, 0, win, 0, 0, 0, minus 1, right? But in general, for a lot of applications, the rewards can be very different. It does not have to be like 0, 1 rewards. You can actually have the rewards. And so technically, a reward is just a sum of these things. Yeah? So you get this reward of plus 1, minus 1, minus 1, plus 1. This is fine. This is the whole sum. So for continuous task, we introduce some other notion of called as a discounted return. Yeah? Which is essentially, it's very simple problem, because if you have a continuous task, if you add up all the rewards, it goes to infinity. That's not tractable, right? So introduce something called a discounting factor called gamma, yeah, which is essentially rt plus 1 plus gamma rt plus 2 plus gamma square rt plus 2. Yeah. So you can think of gamma is some number between 0 or 1, where you downweight the future rewards, yeah, and that's called as the discount rate. So the discount rate actually is the way says that it's the present value of your future rewards, right? And how much are you going to give importance to the reward which you will get in the future, as opposed to valuing your current reward. So as gamma approaches 1, the agent becomes more far-sighted, because it wants to take this in the long run. As gamma comes to 0, it's a very myopic agent that is a very greedy. It wants to do only maximize right now, yeah? And that has a factor of what kind of policies it will run, right? How you set the gamma. Okay, so I talked this policy now, and I called it return. Yeah, so policy is how do I take the action, and return is essentially what do you call, a sum of the rewards you got over the one episode. Yeah, that is for return. Okay, so we're still not there, right? So okay, so the reason is this, right? So what I said is the agent's goal is to maximize the total amount of cumulative reward it receives over the long run. Yeah, this part of long run I didn't put, right? So essentially, you can think of GT is again a random variable, right? Because the reward you are getting is for one play of the game, right? Anytime you come, you take an action, there is a stochastic policy, you can branch out, then there is another stochastic policy, you branch out. So there will be multiple policies, right? So the agent's goal is actually to choose the actions to maximize the expected discounted return. So what we need to now do is actually take an expectation over these different episodes, right? So there is one episode you start, you win. Another episode you start, lose, right? So you run this game multiple times. At each time you get a kind of either a reward of +1 or -1, and then GT is just the sum of that rewards. Expectation you can think of just like do an empirical sum of this, right? What is the average return I get, yeah? And essentially that's the RL framework, is to choose the actions to maximize the expected discounted return, right? So we went from reward, you You went to return, then you said discounted return, then you said expected discount return, and that's what you want to maximize. And this expected discounted return is what is called in the literature as a value function, and that's what you're trying to maximize. Yeah. And this is the most formal definition of what we call as a state value function, yeah, which is the value of a state S under a stochastic policy pi is the expected return when starting in state S and then continuing that policy thereafter. Yeah. So you start at state S and then you play the game. I want to know what is the value of that. That's the technical term for value technique, which is nothing but you start that, you keep track of all the rewards you get, but realize that these rewards are stochastic, so you take an expectation of that. Yeah. And that is essentially the state value function, which is how much reward will I get from state S under policy pi. There is something called an action value function, which I will skip. Yeah. This also I will skip. Yeah. So for now, this is all we need to know because I am kind of running down on time. So you have this policy, then I said what is the return, which is the discounted return. Then I said expected discounted return is the value function, and an RL agent will try to maximize that. Yeah. I'll also skip this part, okay, because we don't really need. I need to come to the deep learning part soon. Yeah. So broadly there are three classes approaches to real framing, which is called as the value-based reinforcement learning, policy-based reinforcement learning, and the model-based RL. Yeah. So now I told you what is the value function. So the value-based approaches start trying to learn this value function. Yeah. Policy-based RL actually takes a different paradigm. They directly try to estimate the policy without considering the value function. And model-based try to build a model of the environment. I think for now let's focus only on the policy-based RL, and that's the one which is showing a lot of success, and that's probably a little bit more hot right now. Yeah. And I covered till now essentially chapter 3 of this book, right? Now you can go ahead and say all chapters 4 to 13 is what is called as the classical reinforcement learning, right? So with the advance of deep reinforcement learning, I can probably safely skip all these chapters and directly come to something called as a policy gradients, right? That's what I'm going to do. But if you are really, you think that you need to understand fully, please free to read all this chapter 4 to 13. That will show you all these classical ways of solving the reinforcement learning problems, yeah? Now we are just going to jump directly into deep reinforcement learning. With this motivation, I think it's pretty simple to see what's happening here, yeah? So again, I'll recall a little bit of notation, right? So for me, it's always this notation. I think that's why I keep putting this again and again. It's always have to be very clear about what are we talking about, right? So that's a goal, that's a reward, which is the RT. Return is the cumulative discounted return over the long run. Value function is the expected discount return. Policy showed you how to take actions. And the agent's goal is to find a policy to maximize the expected discounted return, yeah? So deep reinforcement learning essentially is that, right? I told you there are three ways of doing it: value-based RL, policy-based RL, and model-based RL. So why not use deep neural networks to approximate the value function, use a deep neural network to approximate the policy function, or use a deep neural network to model the environment, yeah? And those essentially are the different things, right? So the earlier successes, that the Auditorium paper came from something called as the approximating the value function. That's technically called a deep Q network or the DQNs, yeah? I'm going to skip DQNs for this entire tutorial. I'm going to focus on something called as a PG, which is the policy gradients, which directly try to optimize the policy, yeah? And there is another algorithm called actor critic, yeah? So if you want to go back and learn again, I think PG and AC are the things you will really want to focus on, yeah? Because that's essentially where they are much easier to understand, and that's where they're showing a lot of potential, yeah? So we'll focus on this algorithm called policy gradients, yeah? So what I said, yeah, so first notion we need to get is that I defined this policy, stochastic policy, which said how do I take an action. So now I need to start to parameterize this, yeah. So I'm going to say that this policy depends on some parameters theta, yeah. And how does it works in our case form? Pretty simple, right? You take your image, in simplest case you could just pass it through another neural network or a deep neural network, or it could even be a CNN, right? So I took this kind of 210 cross 100 cross 3 image, pass it through a deep neural network, it could be a CNN or any neural network, and the output I put a softmax layer, which is either 1 or 0. 1 means I move the paddle up, 0 means I move the paddle down. That gives me a parameterized policy of moving my paddle either up or down. So what is this modeling? Given any image ST, what is the probability that I take the action AT is up or down, right? That is essentially the policy network, yeah? And the whole goal is now try to learn the parameters of this policy network in the reinforcement learning paradigm we discussed earlier. Yeah? So the goal is to learn a parameterized policy that can select actions without consulting the value function, yeah? But technically, note that a value function will still be used to learn the policy parameter, but it's not required for action selection, as in the queue-based, the value-based algorithms. Yeah, those are familiar with that. So again, we'll do the standard deep learning trick, right? So I have a policy parameter theta, which are the parameters of this CNN, yeah? And I want to maximize the performance measure called J of theta. As usual, we'll do stochastic gradient descent. The only thing is this is what you're trying to maximize it, so I'll do a stochastic gradient ascent. So theta t plus 1 is equal to theta t plus alpha into gradient of this thing, yeah? So essentially, the whole literature, probably you can write like 20, 30 pages on what are the different ways of computing this gradient. That's all the policy gradient is about. Yeah. Fine. Yeah. So again now we'll come back to the same, right? So essentially we said we want to maximize the discounted return. So we are going to, the performance measure would be that value function we're trying to maximize. So given a start t, I'm going to play the game and I'm going to get a lot of rewards. How do you want to maximize it? Yeah. So the whole thing is, how do I find the derivatives of that, right? And this is a little bit, I'm not, because lack of time I'll keep this. This probably is the most crucial part on how do you compute the derivative. There are two standard tricks people use, yeah. The one is called as the log derivative trick, and the other is called as the gradient of the episode, yeah. So the log derivative trick actually takes the gradient of an expected value of a function of f of x, yeah. So bear with this. So this is gradient of expectation of f of x is nothing but expectation of f of x plus this term, yeah. This is the trick we'll need to, right? Forget the derivation, but eventually this gives you a way to push the gradient inside the expectation, yeah. And that's very helpful because it helps us to do now the expectation via empirical averages, yeah. The second is actually we also need to compute the log probability of an episode. The way to think about is that I run the game, I get a bunch of states. So I just want to see what is the likelihood of this trajectory, right? So, and that's where all the dynamics of the way you're defined come in, right? So essentially here you say that what is the probability of the first state, and then given this state I take an action AT, this is my probability, that is the policy, and then I take this action AT, I'm in state T, what is the probability that I move to ST plus 1, and this again I'm invoking the MDP, the Markov property, because it does not depend on anything else. So this is all the trajectory, and then I essentially bring the log in and sum it up and take the derivative, and all this it comes up to is that the derivative depends only on the policy. That's probably the beauty of this. Essentially the state dynamics completely disappear. Once with policy gradient, I really don't need to know what is the Markov property, how the states are evolving, etc. All I need is the gradient of my policy network, yeah? And probably that's the whole thing. This is essentially the final takeaway of this whole talk, is this equation, if you remember, right? Which is essentially the gradient of my value function with respect to the parameters theta of the policy is an expectation over the trajectories. When I say expectation, think of that you're playing a game, you got 1 episodes, and you play a game 1000 times, you get 1000 episodes, right? I'm just going to sum that over 1000 times. Yeah, that's how I take the gradient. The interesting thing is these 3 parts. What are these parts? This is my total reward. So I play the game once, I got the reward of 1. I gave the play reward, I got a reward of -1. You're weighting by this, and this is your standard, think of, if you're saying this is your standard loss function, log likelihood loss of the softmax, right? So the interpretation of this equation, I think you can see it in this one, yeah? So this again comes to a standard. So if I think about in a standard supervised learning setup, right? I can think of that I have a CNN and I am predicting 1 or 0, should I go up or down, right? I can actually give you a lot of examples. I give you this image, I say move the paddle up, I move the paddle down, up, down. So that would be a standard supervised way of learning this network, yeah? But the thing what is happening here is that you really don't get supervision at that instance level. All that you get is you play the game to the end. Then you get a reward of either +1 or -1. Now I need to figure out how do I have to propagate that reward back to every action I take. Because right, what you are getting is, for example, you figuring out there's a long run and then this, yeah? I think I'm out of time, right? Okay, let me just end with 1 slide. So I have 2 more slides, I'll just end it, yeah? So the reason why policy gradient is important is that maybe I think if you want to learn one method in deep reinforcement learning, that would be the policy gradient, right? If you want to read up more. And essentially, it's actually much simpler to approximate the policy gradient. And the choice of policy parameterization is a good way of injecting the prior knowledge. There are very stronger convergence guarantees are available for policy gradient over action value methods. So the next step from more advanced topics, if you move next from here, is the equation I showed you actually does not work that well in practice. Yeah? The theory is the same, But you have to control the variance of that. You use something called as a baseline estimator to subtract, to decrease the variance, and that's what you'll find probably papers written on how do I control the variance of the gradient of the value function. Yeah? That's essentially all the literature is about, to get better estimators of the gradient of that value function. Yeah? And then there's a next line called actor critical algorithms, which use both the value function and the policy gradient, which we'll not talk about. I'll end up with 2 slides, right? So can reinforcement learning solve all kind of problems? No, right? And that's what I want to go and think about. What are the other kinds of setup you think probably RL cannot solve, right? So this is one game which is called as the Montezuma Revenge, where it's known to fail very miserably. Here, if you just summarize everything, it's fine, but what is happening is that the key part of the game is that the agent has to figure out that there is some key here. The key will unlock me to some hidden treasures, and I open that, I get some reward. And humans, when we are playing the game, it's very natural for us that key means something, right? So we really don't explore too much, we just directly go to the key. But in order for a machine to figure out, or an RL agent to figure out, it has to run lots of trials till it figures out that hitting the key is the right thing. And that's why there's a lot of, in this game, I think it's very easy humans can do better than RL in this case, yeah? And I think I'll just end with this slide as a thought for you, right? You want to think about, with all the hype and all these, can AI be dangerous, right? Probably with supervised learning, people think it's ridiculous to think of where does AI have any negative consequences. But if you think about now with what I told you with RL, right? So RL can actually be programmed to do something beneficial. But look at it in the end, all that it cares is that I just want to achieve my goal, yeah? And you specified some reward. You never specified with how do I achieve this goal, right? It can actually figure out that there is a very destructive way of achieving this goal. All that cares is that I just want to maximize the reward. I can say that my reward would be that goal is that drive to me the airport as fast as possible, right? You specify it that way that it could probably cause a lot of accidents even before it reaches there, right? Because it really does not have any notion of what is an accident or not. All it cares is one track, that I have to reach to the airport faster, yeah? And that's why all these concerns come on. How do you actually, is just specifying this whole rewards and goals is the right thing to do, right? How do you bring in other constraints? How do you bring fairness? How do you bring morality? Can the agent have a guilt, etc., right? And that's essentially I will end the talk with, yeah? Thanks, guys.
Thank you very much. Our next talk is about generative adversarial networks, which is a really fancy way of saying somebody who creates something and somebody else who criticizes it. But in this case, the somebody is a neural network, not a student and a teacher or a parent and a child. It builds really realistic results because, well, you know, like a student and teacher relationship or a parent-child relationship, the adversarial aspect makes corrections very strong. So, before I get too carried away, I am going to introduce our next speaker, who will do the actual talking about this. A warm round of applause for, where is he? There he is, on the other side of the stage. Ramanand from Semantic 3.
Set up. I hope the mic works. Okay, great. Let's set up. We've got the slides. It's okay. What charger? Oh. Okay, great to be back. Started seeing a lot of familiar faces again, but let's talk in slightly more technical detail today. It's about the Hitchhiker's Guide to Generative Adversarial Networks. Very fancy name, GANs, they seem to be very popular this year also. But let's get started, let's see how far we can understand the space. So most of you might have heard about this, but I work for Semantics 3. We work with e-commerce focused companies. We do a lot of machine learning algorithms, data primarily, and also intelligence layers on top of them. We help them cover a lot of automated tasks like categorization, product matching, automated entity recognition from a product, and of course a whole slew of offerings. Product matching, distributed crawling is one of our strong points, but I guess this is something you might be interested in. The rest of the talk, nothing related to it, don't worry. So okay, let me give you an overview of how today is going to be structured. We're going to start with a generic overview of why do we study generative networks, what do I mean by generative networks, and what are the things that involve. And then there's a slightly theoretical part. Please don't leave. I think it'll be a little bit of math, but should be interesting. About the fundamentals of how adversarial networks are set up, about how GANs themselves are structured, and an introduction to the system. And then this is why I didn't want you to leave, because there are huge developments in the last year. And then I'd like to motivate them through applications of how they can be really visualized. And this should be a whole bunch of demos. And seeing that this is a guide, this is like across the whole space. I'll have links everywhere in the slides, and then hopefully it points you in the right directions. And then finally, GANs are not going to be the most promising thing. I mean, GANs are very promising, but they aren't going to be the solution to everything that you see. So let's look at the issues which are commonly faced. And of course, again, improvements and the path forward, moving up to the research which is being conducted. At least the mic still works, so the slides are there. Okay. Let's look at generative networks, right? So what do we mean by generative networks? So let's get everyone active here. Can you start guessing? On the left, we have I think it's a volcano erupting. On the right side, it looks like hills. Can you guess? This should be slightly easy, I think. Can you guess which one was drawn by a computer and one was drawn by an artist, like a real human? Left, right, anyone? Artist on the right, yes, that's Marvin from Douglas Adams. So Marvin also points out the artist on the right. I think sort of you start guessing that it's too abstract. I don't get it. I'm not very artistically inclined. But yes, that's the bot on the right. Sorry, yeah, so that's the bot. Something harder, maybe? So again, there's one of these was drawn by the bot. And then here I sort of lose track. I don't remember which one was which. So can anyone say? Left, right, left, right. Computer on the left. Very good. Well done. Again, so that's again some study which was conducted, and then turns out people are quite difficult at making this out. So let's go to insane mode. And at this point, I don't know. So both of these look very similar. Apparently, one is like a very expensive painting, and the other is 30 seconds on a Pentium processor. So let's look at this, and then turns out it's the one on the right. And then, so that seems to be, so I hear, if you look at most of my slides, later I have a description to where the slides are hosted. It's on Anthill's website. So if you just click through, you'll be able to see the papers which are referencing this. And then this very recently came out in May this year, I think. El Gamel and his group, they together made this study, and then a lot of people voted on the wrong paintings. So again, these are how generative networks are structured. You essentially want to be able to do forgeries of high-end artwork, make money that way. So why do we want to study generative network? We want to understand and tackle complex information, right? We want to be able to study not just classifiers, not just discriminators, not just tracking performance of numbers. We want to be able to understand if there's any underlying structure behind them. And then most of the time there's like high dimensionality in the objects being studied. So the probability distributions are no longer simple functions of one or two variables. What if we want to dimension it? What if the dimensions are in the hundreds or thousands? We want to be able to model them correctly, and maybe that helps us. Finally, like in the previous examples, we don't want to just model them. We want to maybe generate additional samples based on some criteria. And I think this ties in to the previous talk as well on reinforcement learning, because one of the proposed uses of GANs is to augment the world environment. So say you have a reinforcement agent, and the agent starts learning. Maybe GANs can help fit in and simulate the environment in which the agent learns. So they pretty much tie in together quite nicely at that point. So, generative networks. It's good to study them. And then let me just motivate how they are going to be structured, right? I'll take a very simple example. Bear with me, it's going to get very messy very soon. But then let's take these points. There's a whole bunch of points on this distribution. And then these are the points which we want to model. Think of these as data points which are structured. Now, one way to do it is something called very popular. It's like maximum likelihood. So wherever we see the points being recorded, we adjust our probability distribution function sort of upwards. So later, if you look at the blue line, it sort of models how the points are distributed in that particular dimension. And this is very common. This is a subset, maybe the most popular one, of how generative functions are formulated. Mathematically, you can define a probability distribution function, P, and then the P is based off parameters theta, and then you start describing this P of model, which gives a sample X conditioned on, or it's basically dependent on theta, the parameters. We want to optimize these parameters, do something like the actual operation where we do gradient descent, backpropagation, all those things, but it's basically an operation where you want to optimize the parameters theta. And we want to get P, right? And from P we get this distribution, and from there we get the points. So there are two approaches. P can be either explicitly defined, or we aim to define P carefully. That's the one on the left hand side, explicit density functions. So in that, there are like a whole way of approaches. And then over here at the root nodes, you see all the popular approaches. I'll just focus on a few for now, so that you get an understanding of how everything is set up. So when you look at an operation which like aims to get the explicit probability function, you can either do it as a tractable method. So if you look at DeepMind in the last 1 or 2 years, I think they came out with WaveNet. WaveNet was where you enter text and then it automatically speaks in very realistic audio. The person speaking sounds like it's a real person speaking and not like your old Microsoft bots. They're good now, but the bots which like used to just literally pronounce word by word from recordings. So WaveNet was based on this sort of approach where they had fully visible belief nets, which are very popular, WaveNet, but the problem was that it's based on like a probability of conditioning on every single input. So it was like a sequential learner, which was expecting to model the explicit density function. Another very popular approach is the variational autoencoder, where instead of aiming, so we don't want to get the perfect P, we set another function, which is a lower bound on P. We call that maybe L. And then that variational bound is sort of proven to be optimal in some situations, not in all. But the idea is that you sort of optimize your function. And then variational autoencoders are at that stage where they tackle the lower bound towards the explicit density function. That's the left tree for now. On the right hand side, again, you have Markov chains, which are very similar. They do repeated resampling, and there are two approaches to it. But for now, FBBNs, variational autoencoders, they are very popular because they've been giving very good results as well. Implicit density functions, what do I mean? So instead of assuming that a P exists, or instead of aiming to get the P, the probability function, we just assume that it exists. So we say that, okay, there might be a P, I don't care about the probability density function, I instead just try to get the samples out of it. So again, you have stochastic networks, Markov chains, and then in that aspect, so in that subsegment of the tree, where we assume a probability density function, and then we start generating the outputs of the model, that's sort of where our whole talk is going to be centered on. So we're going to look at GANs in this context. So if you start from generative networks in general, GANs sort of fit in this place where they model the probability density function so many times. I think you just keep count how many times you say that. So that's how GANs are supposed to work. Again, Ian Goodfellow's very popular NIPS tutorial is there on the link. You should check it out. It's much more than I can fit in 40 minutes. So how do we do this comparison, right? So when I reported WaveNet, which is like a very popular model, unfortunately it takes 2 minutes to generate 1 second of audio. So it's like very difficult to use in real life. It's very popular, it gives very good results, but the computational complexity is sort of like a problem. Guaranteeing asymptotic consistency, what do I mean by this? There are of course lower bounds and you expect to optimize it in terms of autoencoders and VAEs. They sort of don't give you the full result eventually. You hopefully get there, but the guarantees are not 100%. And Markov chain, because of their consistent resampling and continuous requirements, they sort of take a long time to converge. If you have played with Markov chains, you realize you don't know how many games to play of the Markov iterations. Again, great description links below. The slides are not exhaustive. Most of these are also based on a lot of existing results. And GANs, again, are not going to be perfect. This is just an example of why GANs do not suffer from these problems. But later on, towards the end, we'll see the problems that they have of their own. So now we can jump into it. Generative adversarial networks. Right. So just to give you an idea, this is like the statistics over the past year. It literally says cumulative GAN, named GANs. So people start calling names for GANs. SIM GANs, Disco GANs, Cycle GANs, DC GANs, so many GANs, right? And then they decided, let's plot a chart. Then even after 2017, you see this right here. It's literally like a zoo. It's like so many abbreviations. that people have no idea what to name their GANs. We are running out of abbreviations for GAN. So if you can think of one, make sure to put a preprint and claim your stand. So let's look at the GAN zoo now. And of course, it was very interesting that last week was the Computer Vision and Pattern Recognition Conference. And turns out Apple started publishing their own research papers. Their first one which came out, which also won the best paper award last week, was on GANs. Figures. So they said, okay, now it works. Maybe it was not selected. So the adversarial game can be formulated with like a game theory formulation. So for those of you who have an idea, it's like a Nash system between two different agents. There's a local equilibrium, hopefully, between the two, which sort of arrives at a stable solution. And then the two names are for discriminator and generator. So one is the forger, the other is the expert. And then they generally are trained together, where they are trained to compete against each other. There are also formulations where you can think of it as a cooperative game, but so far the way of thinking of it as like a agent where two people fight against each other sort of gives an easier understanding. And then each aims to defeat the other. So when you think of this framework, let's look at this picture again. So this is pretty much how you can explain how a GAN is structured together. So let's look at the right side first, where we have this sort of noise. So you can think of this noise as a vector space. Let's just call it a latent vector space, and I'll denote it by the symbol Z. And then this Z is sort of fed into a neural network, the generator, and then the generator has a function, let's call it G of Z, and then it starts generating samples. So it just starts generating one example after another based on some random noise, at least initially. So it starts generating outputs. On the other side over here, you have a sample data set. And all of these are real life images or real life examples. So these are not the fake ones, but the real ones. And then these real ones are going to be where we sample our true values. So what happens is that you have this network at the top. That's our second network. That will be called our discriminator. Then very simply, the discriminator is either fed a real value, d of x is the function then, or it's fed an output from the generator. That becomes d of g of z. So you have d of x or d of g of z. One of them, you feed one or the other into the discriminator, and then it's like a binary classification problem. It either says it's a real image or it's a fake image. It keeps guessing again and again, and then these two systems are what we are going to train now. One of them starts generating, the other one starts discriminating. So let's look at the relatively easier one to think of first, or the discriminator, which is the one at the top. It thinks of whether it wants to determine if a sample is real or fake. So when the sample is from the real set, it wants to say it's 1. When the sample is from the fake set, it sort of casts this function as a 0. So that's like the complication of how it goes about it. This is how we want the discriminator to behave. And then this is a very fancy way of saying the two lines here. So we define a loss function, the j, for the discriminator as a function of its parameters theta. And then if you just close your eyes or squint real hard, you can just see here where d of x is the one which needs to become 1, and d of g of z is pretty much in a 1 minus. So the idea is that by combining these two expectation values, we now have a easier way of defining how the loss function needs to be written for the discriminator. So you can think of this as the final loss which is going to be calculated and back propagated through the network for the discriminator's updates. So we have the discriminator, it's quite straightforward, 1, 0, it wants to discriminate it. Then we have the generator. For the generator, the idea is to fool the discriminator. So we can sort of use like a recursive thinking about it. So what does the generator do? It needs to fool the discriminator, and the simplest way is to just define it as a negative. So you take the discriminator's function, you put a minus sign, you call it for the generator. This is sort of like a min-max game, where you make sure that one of them is able to defeat the other. There are a few problems with this, because you're thinking of them as two separate networks. So if the discriminator becomes optimal, then the generator stops learning. Because one of the loss becomes 0, you put a negative sign, doesn't matter, it's still 0. So you sort of fool the generator into thinking that it's no longer learning. So there are some heuristic motivations to get another way of defining the loss function for the generator, and one of them is this. So g of z, that's the output function for the generator. and d of g of z needs to be 1. Remember, this is different because the generator wants to fool the discriminator. So he wants to convince people that it becomes 1. So you write like a non-saturating heuristic function, and this pretty much says that the expectation needs to become 1 for the generator's output. This is how the generator thinks about it. There are other ways. Like I said, this is formulated in a maximum likelihood type of environment. So you can pretty much cast the equation where you have here like a logistic sigmoid function on top of the outputs. This is just for completeness so that you understand that this is actually functionally equivalent to the maximum likelihood estimators I was talking about. So this is pretty much just a way of recasting it. So you can think of this as like the two popular ways of how to define a loss function for the generator. So now we have two loss functions, one for the discriminator, one for the generator. What do? Stochastic gradient descent, most common. So we take two mini batches. We take one from the real samples x, and then we run the vectors on the generator. We get another batch of outputs. So we have two mini batches, one real, one fake. We pass it through the discriminator. It gives you answers. It gives you ones and zeros. And then based on that, you can simultaneously run back propagation on the two networks. So you calculate the loss for the generator. You use it to update the weights for the generator. You calculate the loss for the discriminator. You use it to update the weights for the discriminator. So it's sort of with each run, whatever loss functions you calculate can be used to update both networks. And this sort of joint training is why it sort of learns together. So for a long time, so this was back in, I don't have it here, but this was back in 2014. I think when Ian Goodfellow and the others sort of formulated this adversarial system. And then for a long time, there was not enough successful computationally easy implementations for them. There are some things called lab GANs or Laplacian pyramid operators, and using that was slightly difficult, and the whole thing didn't take off until much later when we had our familiar convolutional networks and deep convolution networks being applied to them. So this was sometime in 2015 when a group proposed that you take your layers, you make them all convolutional, remove any pooling or unpooling that you have, and then eventually you start doing batch normalization, and turns out the output of these sort of networks was much more clearer, higher resolution, and also easier to train. So just a few pointers here. So what happens here is, this is the network of the generator. So we have two networks. This is probably the generator. So you look here, it takes like a vector z, and then it does a whole bunch of convolutions, like strided convolutions over here. It makes it bigger and bigger and bigger, so you can think of the final output as like an image which has been generated. So this image is then going to go into a more traditional classifier, and then that's the one which starts distinguishing whether it's a real image or a fake image. So this is like the deep convolutional GANs which were set up in order to successfully make it work together. So that's about it. Hope that wasn't too much of technical detail. But now again, we look at very interesting applications. So with that setup of how generators and discriminators are now working against each other, we now have an idea of like the different components involved. And let's just see how that translates to real world applications. And the first thing, which is also from the same paper which I was referring to, DC GANs. And when I saw this, I was like blown away for a few minutes. I had to sit down and think about it. So what happened was that if you remember word2vec and all the complications that arose with it, we look at the example and you see very strong similarities. So when the generator starts generating outputs, people were able to model the ways in which the outputs are related to each other. Let me give an example here. So there were a whole bunch of pictures. All of these are generated pictures. None of them are real pictures. So all of these pictures were generated by the generator for a specific position in the latent vector space. So you have the generator, it takes some noise type of input and then gives these photos of men with glasses. Then for some other point in the vector space, it just gives photos of men. So what do? You subtract it out, and then you can see where this is headed. When you add a woman with glasses from the vector space in the noise, in the latent vector space, the generator seems to be able to transform it like this. So if you remember the word2vec approach, where king minus queen plus man, I'm sorry, I got lost here, but it's sort of the way where you start seeing that the vector is able to identify the important components in each space. And this was something that was quite interesting. It's not just segments of the image, or it's not just lines and edges which are being identified, but it's really the concepts of the image. And this seems to be quite interesting of how the generative networks are learning. There's another recent paper, most of it is going to be this, so I'll just assume that the link will be there. So you take like a very strong image or very high quality image. So this is like a very good painting, I guess. I think it's a painting. And then you downsample the painting. Say it's 1000 by 1000 pixels. You make it much smaller, 200 by 200, like that. And then you put it into Photoshop, and then you run the bicubic interpolation or some simple method. I hope it's clear, but this is very blurry. So this photo turns out that when you approximate each point by the neighbors, you get a blurry result. However, it is possible to take this sort of blurry downsampled images, run it through something which is called an srGAN. So many named GANs. So you run through it srGAN, and then it starts generating much more clear images. So it starts giving high resolution images, which sort of end up being significant improvements over what was previously proposed. So super resolution seems to be possible now. Interactive GANs. So I guess all of us went to school at some point, and then you remember there was this art class, and the teacher said you draw a painting, and then everyone goes to the scenery. Draw a river, draw two mountains, draw the sun. If you're really fancy, you draw birds and a house in front of it. So again, looks like the GANs are beating us at it. So over here, what you see is actually a person conveying his intent over like a vector space, over the noise vector space again. And by simply telling them what colors they want, they're able to do things like real-time editing of images. So by simply drawing a white line, he sort of adds snow to the mountain. By drawing like green lines over here, it becomes like a field. The interesting part was that for each of these updates, it was of the order of seconds. So we are literally able to near real-time edits of the images. So that's about interactive GANs. I think there was another impressive video where they took a photo of a lady, and then they started adding black color, and then the hair changed from blonde to black. Again, very impressive results. So these are like the rough images, but it actually starts generating high resolution images once you let it to settle down. Image to image translation, again, very popular. Most of you might have already seen it. It's also referred to as pics to pics. And then this is sort of what was being done. So on the left hand side, we have inputs. On the right hand side, we have expected outputs from the generator. Again, this is not a real picture of a street with cars on it. A person sort of described how it will look through segments, and then it starts modeling it and starts outputting images which are trained to fake people. Similarly, if you have spatial photographs, say you have a new satellite and it starts taking photographs of the Earth, and then you start seeing roads and maps being auto-generated. It can go even further. It can even start doing impressive results, which are being done in Photoshop, like if you want to convert from black and white to color, if you want to go from a day scene to a night scene, if you're an architect and you design a house and then you want to add where the doors and windows are going, it may look impressive here, but if you zoom in, there might be something very weird about it, but I guess it's part of the process of how these guys are still learning. And of course, you can do things like this, where you draw a rough sketch, and then it starts giving realistic interpretations of how it might look in the given domain. It's a great website over here. You can go up, try it. They have very impressive other models, not just the examples here. Text to image synthesis. So a few years ago, there was a very popular article where you give a photo and then you start describing the photo automatically. I think Facebook even now does it. If you upload a photo to Facebook, it starts telling you, adds keywords to the photo which sort of describe what's happening there. We'd like to do it in reverse here. So what we do is that we start writing sentences, and these vectors sort of condition our inputs. So when we feed to the generator, we sort of add conditional inputs into the vectors, and then these sort of vectors, the text vectors which are encoded in some vector space, they start determining the output of how the image is going to look like. And then even for me, like I couldn't do this right. So you start with describing this, and then it starts coming out with realistic photos of how a bird with a red beak and with like a black feathers standing out there. It's also possible very impressively for flowers and some other aspects. So this is literally translation in the context of going from text descriptions to being able to go to images. Again, these are very cherry-picked examples and all of that, but seems impressive that it even works in the first place. image completion. And what do I mean by this? It's about corrupted images, right? So there are a whole bunch of celebrities here. You might recognize a few, I don't recognize most of them, but you cut out their nose and then you train the network on how to do in-painting over these images, and then it starts to identify that a nose is most probably the structure over there. It starts to match the color and the shape with the rest of their faces, and again, all of these are ways in which the whole system becomes a part of it. So it starts to generate sort of realistic results, and again, generative networks at the center of it. You start noticing a trend. Most of the results are 2016 or 2017. So that's like the last year is when most of the things started happening, and it keeps improving day to day. Multiple GANs, which I think is 2017 now, right now, a few months ago, where stacked GANs, and people are able to describe them as combining two GAN networks. So instead of having a generator discriminator by itself, you take another pair of generator discriminators, and then you put them together and you start training them to identify relationships across domains. So what happens here is that if you go out shopping and then you have a shoe which is in a particular style, then you want to get a bag which matches that style. So they started being able to generate samples which are consistent across their whole catalog. Very impressive results. And then there's a new one. So this was called Disco GANs, and the other one was called Cycle GANs. Don't have to remember the names, but yeah. So there's this horse over here, and they were able to like take a photo or a video of the horse running around, and one network was able to do it convert it into a zebra. So when I looked at this, I thought, okay, that looks like a zebra, but the tails were weird. Turns out zebra tails are not striped, but I didn't know that, so yeah. And then you could also do it the other way around, where zebra could be converted into a horse. So these sort of GANs were able to do it in either way. So you have stacked GANs, multiple GANs, and then it's just going to be all the way down. You keep going with GANs. So very impressive results. And of course, I have a few more minutes, and then I'm going to talk about the issues that were happening, what is the state-of-the-art research, and if you want to go to NIPS this year, I think it's already closed. The papers have been accepted, but most probably they're going to end up talking about things like these. So stability and other problems. Let me just talk about it in brief detail. So finding equilibriums are hard because, like I said, this is not an explicit loss function which is just being optimized. We need to be able to do sort of a joint system where optimizing not just one network but together with another one. So the local equilibrium points are sometimes local minima which you end up being stuck in. Non-convergence has always been a problem, especially something called mode collapse. So what do I mean by that? So say you have pictures of dogs, and then the idea is that you want to start generating fake pictures of dogs. You feed it like a Labrador, a pug, a golden retriever, and then you start teaching it all these types of dogs. But what happens is that, as mentioned like in the few weeks, like the few talks earlier, some people are saying that the network sort of learns to cheat, and it starts realizing that, okay, I will just start generating pugs. And those are like valid dogs throughout. So it ends up that we sort of collapse into like a diversity problem. The network starts generating very, very similar looking examples. And of course, there's one thing which I sort of skipped because it wasn't very apparent over there, which is the differentiability requirements for the loss functions and the whole networks. So you remember our D of Z or D of Z and G of Z, both of them, either of them, the functions need to be differentiable. I didn't go into much of the mathematics, but the idea was that this constrains us to sort of continuous functions which are being output. So working with text has been a problem in this area. So most of the functions or most of the outputs, you might have noticed a trend, are all images. There are approaches which are looking at generating text with realistic results, but none too convincing so far. There are workflows, but let's see. And how do we improve GANs? So stability has been a problem for a long time. I'll just leave all of this here. Okay. So the first few are on hacks on how to improve GANs. The Sumit Chintala has like a very popular repository where he literally lists you, if you want to train GANs, just follow these steps. And one of the idea is that like the first vector space Z in which you start generating the outputs, instead of having it as like a noisy uniform distribution, you sort of have it like a spherical space, and that seems to give slightly better results. One-sided label smoothing, which may be applicable to other domains as well, essentially means that instead of going from 0 or 1, you sort of adjust your labels so that your output is like a 0.8 or a 0.7. This sort of still conveys the information that you are good, but sort of adds noise at the layers. Finally, you also have reference normalizations, batch normalizations. These are some things which are done. By this, the losses which are computed and the intermediate layers, the normalization is done slightly differently. And finally, this is sort of like the big problem with GANs, which people are still working on. It's about stability in all of these systems. So when the two networks are learning against each other, we're not very sure on how stable the outputs are going to perform. So people are looking at different ways. They are continuing to look, almost all of them are 2017, but most of them are still trying on how to ensure that stability is a solved problem. One easy or one effective approach seems to be conditioning on how realistic the output looks. So how do you judge the quality of a fake image, right? Everyone has their own opinion. So when you start judging the quality of fake images, people started defining it using other distance functions. Like this Wasserstein was one of them. So you start defining other loss functions and other distances based on that, where you make sure that the realism of the image is sort of an important parameter. There are also autoencoder approaches like BEGAN and BGAN. Okay, that's actually a word now. So BGAN, and then these approaches sort of like help define or help set the stage for stability problems to be solved. Quite sure there are a lot more to be covered, but I'll leave all of these here. So that was the guide to GANs. You can visit this link for the slides and the content and all the references. Hopefully it's useful. I just wanted to give a presentation on all the overview. Maybe hopefully it's useful when you start searching off. Hitchhiker's Guide to GANs. That was me, Ramadan, and thank you very much.
We'd love to offer you a few minutes for questions and answers. If you have a question, please raise your hand. We'll get you a mic. Whoa, I've got two right down here. I'll give you a mic. Please stand when you give your question and identify who you are. We are doing a live stream.
Hi, thanks for the interesting talk. I'm Vipul. So my question was around, you said that the differentiability requirement is causing problems with discrete outputs. So that applies when I'm trying to go from, say, text to text. So you can't do my homework yet. But so what about other forms of continuous outputs? For example, so images is one, but what about, say, graphs or, time series and things like that? So have there been areas like...
I think there have been few approaches, especially like at the start where people are trying to generate audio-based samples, or even for images, right? You can think of it as, so essentially the pixels are going to be numerical values which are being generated. So I would think that if you want to solve problems which are time series or value-based, the same encoding system, or again, I don't remember of any specific approaches which I worked, but if you look at an image, when you actually type it out, it's going to be a series of numbers, pixel values. So I think that might still work, and those are not discrete yet, but quite sure it might work. I can't remember here of any specific examples.
Our next question is over there.
Hi, Shamir from Morning. So when you showed the equation for this, when you looked at it for the degenerative equation,
okay,
so it's either log, when you said it's only binary.
Okay.
So what if the probability is an equal percentage? So does it again go back into the network? And in the
yes, so I didn't talk about how the network terminates. So what happens is that when you start off initially, the discriminator has like this option between 0 and 1, and the whole structure is based on whether the loss is like a finite value. When the discriminator becomes confused between a half, so it says x is half, z is half, that's sort of the end stability condition. That's ideally when you stop the training. So what happens is that at that point, you're at the place where the generator is like completely as good as it can get. And then that's essentially the stopping condition. So if you have the output of the discriminator stuck at half or 0.5, and then it cannot differentiate between the real and fake images, that's at the point where you start seeing that you stop your condition, and that's sort of the end state of your training. Yes. Yes, so the equilibrium condition is exactly that. The equilibrium condition is that the discriminator fails to generate any difference between the two images.
All right, our next question is right here in the middle.
Right? Yeah. Thanks for the talk.
Solving classification problems. It might not be trained explicitly on the classification problem that you are trying to solve, but again, there's definitely some amount of transfer learning or some amount of pre-trained weights which might be useful. I'm not sure, but I'm quite sure there are, but off the top of my mind, I'm not sure. Yeah, but it's definitely something we should look out for.
We have a question way in the back.
Hi, great talk.
Okay.
Yeah. So my question is like there are two parts in GAN, right? So one is generator and the other one is discriminator, right? So most of the applications which we saw was from the generator part. So is there any like can we use the discriminator part for like building something?
Exactly, I think that's exactly what the previous question was also about. So I think the utility of the generator is what has been discussed so far. I also strongly believe that the discriminator could also be used, and I think most of the times when you want to use the discriminator, it's sort of not in the image context but maybe in a classification context, and some of those are quite useful. We have not seen anyone try to use the discriminator for like ImageNet classes or anything like that. But I think for simple binary operations of like deciding whether an image is of a particular class or not, I think discriminators are still able to do quite significantly. Whether they have been used anywhere so far for any classification problems, I'm not aware of any. Yeah. Okay. Yes.
Hey, Ramana.
Yeah.
Hi, great talk.
Thank you.
This
Yeah.
question is more on the ethical sense. Like recently, you might have come across all the fake news like Obama's.
Sorry, I can't hear you very clearly. Maybe slightly closer.
Hello.
Oh, okay, better.
Hey, Ramana. Great
Yeah.
talk. So this question is more on the ethical sense. Like you might have come across the recent fake news generation, like Obama's speech has been morphed.
Okay.
As in
Yes.
what we can do. So how GANs are like helping in tackling this fake news challenge, or are there any countermeasures to handle such fake news that are getting generated using GANs? Like, have
So
you come
do you
across-
mean for speech-based inputs for GANs? Because text-based filtering, I'm not aware of any good results because of the whole problem with discrete inputs and discrete outputs.
Right.
But for filtering of voices,
Are there any ways like we can identify this is generated by computers so that the fake news can be tackled in the future?
possibly, hopefully, you get a network which is, so again, this involves using the discriminator component,
Yeah.
I think, yeah. So in the discriminator component, if you have a generator which is aiming to model the fake news part of it,
Right.
quite sure that as long as you generate your samples consistently, it might be able to, the encoding into a representation of what a fake news represents is the actual problem in my opinion. So getting the representation right might be an issue.
All right, we have time for one more question. And we have a question down here.
Yeah, I have a question.
Okay.
This could be the same as seconding his ethical question. One way you are talking about, I explain about the thief and you can draw that using GAN. But at the same time, when I look at the disco GANs, I see that the horse is being changed to zebra.
Okay.
So I can actually put some some wrong person in the same video. Usually in the judiciary system, we kind of rely on the videos as well. Is there any kind of regularity on this kind of entire research, the implementations and the research?
Good question. So far, there have been very convincing results. I think a week ago, someone made a picture of Obama speak very realistically, things which he never said. The legal issues are still a minefield. I have no idea on how people are going forward. There are few organizations which are looking at it. EFF, the Electronic Frontier Foundation, OpenAI to an extent, all of them are looking at the ramifications of how reinforcement learning systems, GAN systems, generative networks, how all of these fit into the broader context of how it might cause issues. We're still not sure. Some people are convinced that it's going to destroy the world. Some people are convinced that it's merely a pet project. But we still need to have reasoning with the entire society. It's no longer computer scientists who are going to determine these things. But yeah, it's too soft of a skill for me to think about, yeah. Yes, yeah, true.
This is such an interesting topic, and I think we could probably have questions all day long. Ramanan, would you take questions offline during the break?
Yeah, sure. I'll be here the rest of the day at least for a while, and then be happy to meet you anywhere outside also.
Fantastic. Well, it's time for a break. Before you guys go out to get your chai or coffee or whatever caffeine you need, I'd like to let you know that if you are on Slack and you are on the Friends of Hasgeek group, there is a special channel called Anthill In where you can back channel questions and things to each other during the talks. So please join it if you are on Slack. And we'll be back in the auditorium with everyone at 11:30, so come back a little early if you want a good seat.
Check. It's working?
Hey, welcome back. While we're all filing in and finding seats, of course, there are announcements. At this point, you probably have a paper feedback form, either from the banquet hall downstairs or from your seat here. If you do, in this minute or two before our talk start, is a great time to review the talks you saw this morning. We will happily collect your feedback so that we can make this a better conference next year. And speaking of next year, do you know that we already have the call for proposals open? So if you're hearing interesting things and it's making your mind go, ping, I want to talk about, well, you can propose your talk so that we can have it next year. Of course, if you're talking about GANs, you might want to wait a little while because it seems like that is moving in a very brisk pace. If you have not yet joined the Slack channel and you liked the music that you were just hearing, Abhishek posted a link to our Spotify playlist. So, you know, there's your really good excuse to get on the Slack channel. Plus, you can gossip among your friends. And yeah, I think we're ready for our next speaker. This is a sponsored keynote by Intel, who's also doing a workshop later in the day. I'll tell you more about that in a bit. We are pleased to welcome Milind, who is the Director of Developer Relations Division at Intel, focusing on IoT and the data center. He's going to tell us about Intel's view on the future of AI from both a hardware and a software perspective. Welcome, Milind.
Thank you. You guys can hear me in the back? Okay. So I attended the first two sessions, and I have to be honest, the last time that I saw so many formulas in a presentation when I was in a grad school, probably around 15 years back. Okay. So this talk is going to be slightly different. At Intel, I lead a developer relation division group, which predominantly talks with the software companies who are developing products, and then the end customers who are deploying those products, and particularly in the areas of data center and then artificial intelligence and the Internet of Things, and how to tune and optimize their solutions on Intel hardware. So many a times when we talk to our developers, they're saying, hey, what's coming from Intel next? What kind of a hardware is coming? And here is my use case. I'm trying to do a video analytics, and I'm trying to include a deep learning and a machine learning. And I want to do a little bit of analytics on the edge. What kind of a hardware that I should be looking into? So what I'll cover over the next 30 minutes is what kind of a hardware that is coming from Intel for a variety of use cases. Many people, may or may not know that we do have a lot of software libraries as well. Okay, so I'm going to touch upon all that, and so as a developer, what is that you can take advantage of that without really worrying about the features in the hardware, without really worrying about writing your own code, but use them, and then faster you can go into the market. And then at the end, I'll also cover a little bit about how do we work with the ecosystem, and we do have several programs, and we have one of the largest developer developer programs in the world, and so we'll cover a little bit on that. So it's going to be slightly different than what you've heard the first two. Okay, so how many of you have seen a movie I, Robot? Okay, I think most of us, right? So I saw it too, probably around 12 to 13 years back, and I mean, if you guys remember, particularly there's one scene. Okay, and by the way, the movie is about robots, and then there's a scientist and then who develop robots. They're intelligent, and then one of the robots basically breaks the commandment or robotic commandments, and then basically become a rogue. And there's one scene that I remember vividly, is where Will Smith is going in the tunnel in his autonomous car. Okay, and then he's actually talking to the car or computer, and then asking some data which he's investigating on the death of that particular scientist. And so he's talking, and then he's getting answers. And suddenly, there is a couple of trucks come, and then he presses a button in the car, and then the car asks him, "Are you sure you are going to do the manual drive?" Okay? And then he says yes, and then he takes the control of the car, and then rest follows. This was a sci-fi, probably around 12 years back. It was a science fiction even around probably 6 years back. But if you really look at now, it can actually become a reality. And we are seeing, particularly in the automotive driving, as one of the key segments for at least our growth. And without artificial intelligence, it would not have possible. And the movie, the plot, everything is in 2035. And if all goes well, and then we all do our job well, hopefully we'll be able to bring it back by 10 to 12 years. That's the thing. Now, okay, so why it's happening right now? Artificial intelligence has been around for a while, but if you really look at it, the hardware capability was not really there to really take advantage of and then put it into the use. But if you really look into, thanks to the Moore's law and then the hardware innovations that have happened, we are now able to really see and then train the models, and then in the time frame that was acceptable, it's acceptable, and able to really move this particular artificial intelligence around. Particularly data. So you need quite a bit of data, and the advent of IoT and then the various of the smart devices around the world, which may be almost around 30 billion devices that are coming in, generating all sorts of data. The data available to train the models to be accurate, really has been increased quite a bit. And we really see that some of these innovations are really driving, the usage, different usage models in the AI space, we've seen some of these major transitions, at least in Intel, we see that, from mainframe to traditional x86, and then x86 standard-based servers into the cloud, and then we see that this artificial intelligence workload is the next big one. Today, when we see the overall number of servers, deployed in the world, around 7% of them, they are running the machine learning and deep learning workloads, okay? Out of that 7%, around 60% are running the traditional ML workloads, and then the 40% of them are running probably the deep learning workloads. It's very, very small compared to what's possible, and we envision that the AI compute cycles, it's all the way from training to scoring to inference, and then at the edge and then at the cloud, we're going to see almost like a 12x a growth in the pure compute, okay, that the artificial intelligence workload will run over the next few years. Okay, this is just some data points. It's staggering. The people who are sitting here, probably checking their WhatsApp and then tweeting or looking into video, typically generates around 1.5 gigabytes per data per day. It's 1.5 gig, right? And thanks to the 3G and 4G, the consumption of the video and the amount of video calls that we do, etc., is really contributing to that. But if you really compare that to a smart hospital, okay, you're almost talking about 3,000 gigabytes per day, okay? And if you look into a self-driving car, the one which I talked about a few minutes back, that's going to generate 4,000 GB per day. So just imagine, and all sorts of structured, unstructured, somewhere in the middle, all kind of data will be generated. And if you consider some other use cases, it will be even more. So this is going to really grow, and then AI, with the help of the compute and the software innovations and the work run around, is going to really accelerate significant amount of the challenges or solve problems which we would have otherwise would not have thought of closing. And if traditionally it would have taken like decades, with the help of artificial intelligence, particularly in the areas of finance or healthcare, I think there's one more track that's going on in the healthcare, is going to solve that problem in a much faster way and to really help all around. Okay? And particularly if you look into India, okay, and as I said, my group works very closely even with the government agencies, a lot of software companies, and then I'm also part of the NASCOM, product council, and so we work with several deep tech companies in the areas of machine learning and deep learning. These are some of the areas at least where we see a lot of opportunity. Okay, if you are looking into the government, security. I'm not sure how many of you know, but government has actually done 109 smart cities, okay? And, multiple are already happening. And one of the key, usage, or one of the key things in the smart city is a DSS segment, which is a digital surveillance security. And our team is working with multiple software companies who are doing video analytics, okay? And today, most of those video analytics is predominantly a traditional analytics where you take an analog camera or IP camera and then you do something. But in a few years, once the smart cities are there and developing, you will see the machine learning, deep learning algorithms coming into the both edge and the server to really make it even more meaningful. So I think this is one of the areas where we see, and we are already working with many of the companies who are into this. In addition to that, healthcare, I think in India, there are around 300 or so startups, which are working on machine learning and deep learning, and healthcare is one of the key things. And if you look into India, people are calling it as the diabetes capital of the world. The amount of cancer patients and the heart patients is going to increase significantly, thanks to our lifestyle and the vadas and the bhajiyas, etc. I think healthcare is going to be one of the very important factors. I think somebody was telling me, when I was talking, that there is a company in India which basically takes the photo of your tongue and then do some image recognition, etc., and tell you whether you are anemic or not. Okay, and then similarly there are so many different such companies that are going to come out. It's going to either predict what's going to happen or give you a personalized care. So healthcare is going to be one important factor. The third one, what we are going to see is a huge opportunity, particularly for India, is IT. Particularly on the chatbots and all the customer. You don't really need to go in and talk to a human being, and 24/7 you're going to get work there. So those are some of the segments where we are seeing important, and it's no different outside of India as well. So I'm going to skip this. I think I already talked about a little bit. Let me go right into where we come in. Okay, so in Intel we are calling it as a virtuous cycle of growth. What we are seeing is, with the huge amount of devices that's generating data, that's pushing all it back to the data center to go and then analyze. And the more analysis that you in the data center, and then you make really, give value to the users, again, that's pushing more and more end devices. So this is going into virtuous cycle, okay? And this is a huge opportunity, at least for us. And what we are seeing is some of the technologies like 5G, which is already there. We are already working with some of the players. That's going to really revolutionize, particularly the use cases such as autonomous drive. Okay, so if you look into us, we are having a portfolio all the way from hardware to software to communication technology, which is going to be very critical in deploying, whether it's a training, whether it's an inference, these AI solutions and technologies, in the world. So just to give you a few, examples, in the hardware space, traditionally, there are specific Xeon servers which are running a typical x86 machine learning, deep learning algorithms. And there is a many core architecture, which is we call it a Xeon Phi, which is the smaller amount of cores, but many of them, and which can really take advantage of the huge parallelism and the vectorization, if you can do, and then get you much better performance, particularly from a training side, etc. And then, if you're really looking at the low latency, particularly when you're getting stream of data, which you have to really crunch and then do something about it in like stock pick, etc. And that's where, a very low, the hardware such as FPGAs, which is a field programmable gate arrays, might be a more, useful there. And then finally, if you are looking into the edge, for example, I talked about the video surveillance, where you actually have to do some kind of analytics at the edge. We do have some hardware out there which is going to do it for you. So in general, it's all the hardware. And then software is going to be very important. So we have done some acquisitions, in Saffron, which is a reasoning system, and then we started to, incorporate them into us. And then we are also, looking into some other companies like Nirvana. And Nirvana is one of the world leaders in ASIC. They are going to have a specialized hardware which is, speed up your training, model of the training quite a bit. Okay. So across the spectrum, and then we are also working on the 5G communication, which is going to be important, and then the memory. So just to give you an overview of what kind of a, portfolio that we have, that a developer can take advantage of it. Now, when we talk to the developer, they say typically bunch of the, pain points. They're saying, look, hardware is changing. We may not understand the complete, technologies that are coming into the hardware. And sometimes, when we train, when we deploy into the customer, maybe they're having a different hardware. So, they may not be really skilled in optimization and really going that deep level and writing that, the code. The second thing they say is, hey, I'm developing a particular AI solution, but I have a core algorithm and I'm very skilled onto it, but I do need these specific libraries which I may not have, which either I matchmake with some of the other ISVs or an optimized library that I can make use so that I can focus on my algorithm and then develop my use case and not have to worry about all that. So that's a typical other thing that comes to us. The third typical pain point that come to us is, I'm not getting any performance and my training time is taking way too much time, etc. So what we have done is, we have kind of looked into that. So typically a developer, if you look at it, is on the top. He's basically creating a use cases or an application. And then, if you look into the 4 levels below is where, we see kind of a hardware. Okay. So I talked a little bit on the hardware side already. So I'm not going to worry about it. And we continue to, come up with a new hardware, over the next few years. And then on top of it is our libraries. So not many people know that we have a holistic set of library. For example, we have got our own Python distribution. So all the sci-fis and the num-fis, we have been optimized on our hardware so that it can take advantage to give you much better performance. Intel DAL is basically data analytics and then acceleration library, which takes to a traditional machine learning, stuff like a pre-processing, for post-processing analytics. We have taken a bunch of those and actually optimized for the underlying hardware here so that you can directly write onto that. Okay? And then the next one is basically the math kernel library and then the math kernel library DNNs, which we call as the deep neural networks, MKL and MKL DNN. These are those real primitive, algorithms which really require writing it right into the hardware, right into the instruction sets that are available in the hardware so that you can get the maximum performance out of it. So there are multiple of these primitives and MKL DNN is actually open source. One can download and the data is available. I'll tell you where you can get all this information in the next few slides. Intel MLSL is basically, a scaling library, right? So if you really look into the training, which is going to be extremely compute intensive, many of the people are also looking into a cluster of machines where they train. For example, if a particular single node takes, n hours to, basically train your deep neural network model, if I have an 8 node, if I have a 16 node or 64 node, the time to train is going to be significantly lower. okay? And so as a developer, what you need to do is to basically make sure that the training model actually scales very well as you increase the number of nodes, right? And as you increase the number of nodes, your total work that is getting done by a node will come down and the communication will increase. So you need to take care so that you get the scale. So this particular library, what we have worked on is optimizes that. So you as a developer don't have to worry about all that. So we will take it care for you. And then the Intel Nirvana graph, it's going to be a new one. It's not yet out there, but it's actually a graph compiler which is going to take your data flow and then compile it into a hardware agnostic, thing. So that's going to come out a little bit more sooner. So, these are some of the examples of, the software libraries that are available. So check them out. In addition to that, people typically don't write even that to that level. Most of the, at least ISVs or most of the customers that we go into, they're all looking into frameworks, right? These are the, frameworks that are pretty much everybody know, like, the TensorFlow and then the Caffe, etc. So we have taken those and actually optimized on the Intel hardware, okay? So if you're using a Caffe, all you can do is, go and then get an Intel optimized Caffe, and I got a couple of use cases in how we are able to get the performance, and you'll be able to get the performance on your hardware, assuming that you're running on Intel hardware, okay? So all of these, we have taken advantage of that, Theano, Torch, Caffe, TensorFlow, etc. And even, I don't know, not sure how many of you know, in Japan, Chainer, it's one of the open source, framework which has been highly used, and we are also working on that one. So again, something for you to go and look into if you're already running it. Are you running on an Intel optimized Caffe? If not, go and then get it so that you can get some performance right there. And then on top of that, we do have some special SDKs, okay? And we have got something deep learning SDK. I'm not going to many detail, but then you get an idea. We have got a CV SDK with all those primitives already implemented and optimized on hardware. And then, we just released something very interesting called as Movidius. Movidius is one of the company that we acquired. It's a deep, it's a compute stick. Not sure if you guys have heard about it, but it has got a compute stick which can plug it into your laptop, and then it has got a CNN optimized and everything. If you want to do a quick prototype, you are able to do right on your laptop. So that compute stick got available recently. Okay. So one thing is, just if you are running on Intel, go in and check these guys out, and then so that you can get a much better performance. Some case studies, I'm not going to the detail, China, a cloud service provider, video cloud service provider that we worked with, they were basically using adapted open source BVLC Caffe with the CNN framework. And then when we worked with them, and then basically, with the using of math kernel library and also Intel optimized Caffe, we are able to decrease their training time by 30x. I mean, this is not simple like a few percentage, but actually you're going to see a much better performance when you use some of those. This is the second one. Again, if you look into on the left-hand side, this is a combination of a hardware and software, right? Because we have many customers who are using different level of hardware, the SKUs are different, etc. So if you look into the leftmost thing, it is using a 2-socket, which is a 2-processor Xeon processor with F2 BLAS. And then when the second line is basically when they use MKL, which is a 2017 version of MKL, they're going to get straight away 3.5x performance improvement. And then when they went to the newest hardware, which is the next generation of hardware server, and then use the MKL, which is already optimized for the newest hardware, they were able to get even further 2x, so almost like 8x from the from the beginning. And then when they went to the third generation of server, which is the latest generation that we have, they're able to get almost like around 18x. And this is the, these are all actual use cases that we have. So again, a combination of a hardware and software can make a lot of difference for you. And so make sure that you look into some of those, so that particularly if you're having a challenges in the performance area and then getting real time, whatever your goal that you have, and then you'll be able to get those. One of the use cases that we are very, very excited about is an opportunity in the autonomous drive. As we speak now, we are working with BMW, which is one of the a big company, and also we are working with Audi. Recently we announced that we are going to work with Audi and other car makers, and we have seen that this particular segment is growing faster than we actually think. Recently we also announced that we are going to look into procuring, getting a Mobileye, one of the Israel-based company who are the world leaders in some of the lidars and then the vision-based thing. But if you look into how I can use this end-to-end use cases, where there is inference in car, okay, what we call as a software-defined cockpit, which is going to be in the car, which is going to do some of the compute, and all the way the models and everything which is trained in the back end, and then so that, we have some of these technologies that can be used end to end. And in the autonomous driving particularly, the communication in the low latency is absolutely critical, because the car has to take really, a decision right away, whether it's, a person or a dog or a cat or somebody is driving. All those are going to be very, very critical, and the latency be critical. So we are spending quite a bit of time 5G, and then go from there. So this is just a one end-to-end use case, how you can take the plethora of the technologies from software to hardware to compute and then the connectivity, and then basically get your use case driven. And this is just one example. There can be many other examples, going forward. Going into the little bit more details into the hardware itself, sometimes it's not just one particular hardware, but also you can take combination of a hardware to get, your models trained. So just a few examples. On the top one side is the training the models, and then the bottom is the inference. For example, if you are training a simple machine learning, then you can either go for any Xeon or Xeon Phi. But if you are going with the many batch models in the real deep neural network training, then in addition to the Xeon Phi or Xeon, we are also coming up with a specialized ASIC from a Nirvana. So this particular ASIC is highly optimized to bring your training time quite a bit. Okay, so this is going to come out, and which we are calling it as a lake crest, later this year. Okay, and then you'll come to know more about it over the next few years. But we are really looking into that ASIC to reduce the training time. And if you look into the inference, which is in the bottom, if you don't really need a real time, then you can go with probably an FPGA plus a Xeon. If you got to have a day to train and then put in the model, it's not really real time. But if you really look into the real time, that I need absolutely low latency, and then for example, just a stock prediction, and if your stream of data that's coming at you, high speed, and then you go to really make sense of something really fast, then something like an FPGA with a really highly optimized algorithm, we're going to give you, a much better performance. So I think there are various of these models that you need to look into. And when you're actually developing or deploying end customers, typically those are the questions that we get asked a lot, is in, okay, what can I use? What is available? How can I bring this time? Typically they come up with a problem, and we go and then try to help them with what architecture and what technology that we have. Okay, so this is the next version. So the Lake Crest version is going to come later this year. But as we move along over the next 3 years, one thing what we are trying to do is the specialized ASICs, okay, which are highly optimized with the deep learning, machine learning, thing, we are going to integrate right into the Xeon, die. Okay, so you'll get to see that integrated, acceleration that is coming in, and we are expecting that almost a reduction of 100x in the training model itself. So you'll see a lot of those coming in, and then more information over the next year or two. But watch out for some of those real innovations or changes that are happening in that field that might be interesting to few of you. Okay. Now this is basically about the product, but my day job is to work with the software ISVs and then the companies that I talked about. How are we working with them, and then how are we working with the ecosystem? And over the next couple of slides, we'll talk about that. Most of the information what I talked about, we have one of the largest developer program called software.intel.com. This is the where we are working with almost around 6,500 ISVs worldwide, and over 20 million developers come to that website. Okay, and we have various different modules in addition to obviously artificial intelligence, which is going to be hot. We have got technical computing, which is HPC and modern code, and we have gaming, we have Internet of Things, various of these different themes where developer come in and then get educated. We also have a lot of sample codes. We also have a lot of tools that you can download and then try them out. And you also have a lot of forums wherein you can actually post your question and get answers pretty closely. Okay, so this is a one-stop shop, software.intel.com. If you're not known, if you don't know about it, go in and check it out. But if you really look into AI, okay, I talked about some of the hardware, software. If you want to go and say, hey, I'm interested in DLSDK or the CVSDK, what can I do? And this is one of the areas which we are calling as Nirvana AI Academy. And this is again a portal where you can go and get all those technical content available, right from the videos, the blogs, and then you're going to get a lot of white papers, the code samples, the tools, libraries, everything. It is there in the AI Academy. And also there is a free, and then there's also a member. Again, it's free. You can actually become a member and get a lot more additional resources and get direct connect with some of the people within Intel. Okay, again, if you're really interested in it, the tools, the community, we already have a lot of developers already on here, so you can go and then check it out. Another program that we run, I think we've seen quite a few success over the last few years, is what we call as the Intel Software Innovator Program. So a lot of these software developers, they're actually very active in the community. They're going and then doing a lot of meetups and then doing that. So what we do is we basically make them under this program. We have around in APJ alone, which is the Asia Pacific in Japan, which I run. We have around 30 odd Intel innovators in there. And then out of it, in India alone, we have got around 20, okay? These guys are typically the guys who are very interested in understanding more, and they get a lot of benefits by becoming an Intel software innovator. For example, they're almost like an NDA wherein we give them a lot of early technology, some of this stuff, what I talked about, we give them, almost like what we give it to our customers, etc. So they will know what is coming in. They'll also get a remote access to our hardware. So we do have a bunch of clusters that are available. So if you want to try it out, you can be an innovator and then get access to that hardware and then run a bunch of your experiments on top of it directly. We also get the tools, and then we also get a lot of this technical content. That's a very thing. The second thing also you get is a lot of notoriety and exposure from a brand perspective. And if you want to know in that community of innovators, everything. That's another one. And then if you really, going ahead and then, attending some of these meetups and another thing, we also support you. So if you're not aware of it and if you're interested, you can check it out. It's again Intel Software Innovator. I think we are going to have around 2 to 3 innovators here today. If you want, you can talk to them about it and then see, if you're interested. I'm not going to cover quite a bit. We do have a special thing for academia. I'm not sure how many people are here from academia, but there is a slightly separate program that we run. Again, it's a very, very similar. And then, again, this is for the student ambassador. So, finally, again, I told you that in the beginning, it's a slightly different talk, wherein I'm going to touch upon you with, what is Intel's vision, where we see some of the opportunities, particularly that where you can develop some of your solutions, etc. At the same time, what kind of innovations or what is the idea that we are doing, particularly around the hardware, on which predominantly most of these artificial intelligence workloads, both the machine learning and deep learning kind of are run. Okay. This afternoon, there is a very detailed technical session. I just gave you a very, very 50,000 feet, wherein one of my co-worker, Mukesh, is going to come and really dive down into all these different things. So if you're not aware, you can check it out. It's at around 3 p.m. This is going to be almost like a more than an hour workshop going deep into some of these aspects that I talked about. And then again, this is going to be really, really exciting. If you've not seen anything in the last 3 to 5 years, I think the next 10 years is going to be one hell of a journey. So I'm glad that you guys are all part of it, and together we can make something happen. Thank you, and then hope you enjoy the rest of the conference, and then good weekend. Thanks, guys.
Thank you very much, Milind. You did such a good job talking about your tutorial that you took away my best announcement. The only thing he didn't say about his tutorial at 3 o'clock is where it is. It's downstairs in room 1, which is just adjacent to the dining area. We're going to be setting up some chairs for our next session, which is panel discussion. And while that's happening, I'd like you all to stand up, please. I'm going to put my mic down, and we're going to do what's called a brain break to reset your mind so that you are ready for the next topic. So the chairs are, as you can see, being set up. I want to talk to you a little bit about the format of the next session. So it's a panel discussion, which means we have panelists. In fact, we have 5 panelists today. And this is also going to be an off-the-record session. Off-the-record sessions, or OTRs, are not live streamed and not filmed.